Hello there, it's Ligaya from Boost Revision, and welcome to this live stream revision session today, looking at the practical that you need to know for the the OCR and Edexcel exam boards on determining the moles in a reaction. So if you're joining live today, please feel free to put any of your questions into the chat box. Some of you may be joining on Zoom, others may be joining on YouTube. Feel free to put your questions in either of those chat boxes, and I'll do my best to check it regularly and answer your questions as we go along. So what we're going to do today is, first of all, take a little bit of time just to review the main moles equations that you'll need to know in order to apply those equations to the practical questions. And then we'll go through an example of two different types of practicals that you can use to measure or determine the moles that are reacting in your equation. So this is a practical that's usually done early on in the Year 12 course. So the actual content shouldn't be too difficult for most of you if you've already started your A-level course, and it may even be a nice little bit of revision. Just so you know, we have already done 3 of these sessions that didn't go live on YouTube, but they were in our chemistry clinic subscription. We will be putting those up on YouTube in the coming weeks. That was on enthalpy determination, synthesis of an organic liquid, and synthesis of an organic solid. And from now on, we're going to be going live twice a week. Once will be me on Wednesdays, and on Sundays, Dr. Owusu will be going live. And for the month of May, we'll be going through all of the practical sessions, all of the practical activities that you'll need to know for your exam boards. So without further ado, I've just seen a question. Is this live stream suitable for year 11s who are thinking of doing A-level chemistry? Yeah, as I said, this practical today is normally done early on in year 12. So this would be one that's quite suitable for year 11s thinking of doing A-level chemistry. It might be, you will have already learned something about moles in year 11. So you may be able to apply some of what you already know. But it will also be a good indicator for you of how you might find the A-level stuff. So as well as looking at the practicals and the calculations relating to that, we will also be looking at some of how you evaluate the practicals and figure out how much error there might be, and how to kind of evaluate whether your practical was valid and accurate. Okay, so without further ado, I'm going to share my screen with you so that you can see what I'm annotating on. Please do let me know at any point if there's any problems with the connection or you're not able to see what I think I'm sharing. So hopefully you'll be able to see my screen now. It just says moles determination. This is the OCR practical activity 1 and the Edexcel core practical 1. It isn't a specific practical in the AQA specification, but it is something that you will come across, and these calculations of moles are very important to be able to use in a bunch of different contexts. So we're just going to start off with a quick bit of revision on the 3 main moles equations that you're expected to be able to use throughout the A-level chemistry course. Some of these you may have already come across at GCSE, but these are the ones you'd need to be able to apply at A-level. So the first one is the moles equation involving a mass. So this is normally the first one that you'll come across, and it's normally used when you have a solid or a gas, which you can measure the mass of. So to find out the moles of something, we're looking at this top equation here. It will equal mass divided by mR, which is the relative atomic mass or relative molecular mass of the molecule or formula that you're given. So if you're looking to find out moles, you take the mass that you have and divide it by the mR, which you'll need to calculate using the values from the periodic table for atomic masses of the elements involved. But you can also rearrange this triangle. So this is the triangle that most people will learn, and then you just need to be able to rearrange it in these 3 different ways so that you can find moles or mass or relative molecular mass, MR. So just be able to manipulate those 3 different ways. So this is the moles equation you need to know if you have a mass that you can use to calculate. And assuming you have a periodic table, you can use that to figure out your MR. The second moles equation involves solutions. So if you have the volume and the concentration of a solution, then you can work out the moles of that solution. So something to note is that the volume must be in decimeters cubed in order for this equation to work correctly. And often in the exam questions, you'll be given volumes in centimeters cubed. And so you'd have to make sure you remember to convert that to decimeters cubed in order to get the correct answer for your moles. So moles equals the volume times the concentration of your solution. Or if you know the moles and the concentration, you can find the volume by dividing moles by concentration. And finally, if you need the concentration, then you can do moles divided by volume. So this is the equation that you'll come across if you ever do a titration. And the titration is another practical that we'll be going over in the coming weeks in our series of live YouTube sessions. So keep an eye out for that if you're interested in titration. So this is the second moles equation involving solutions, and you need to know volume and concentration. The third moles equation is involving volumes of gases. So this is specific to gases, and this relies on a law that states that a gas, or any gas, at room temperature and pressure, if you ever see RTP written like this, what that means is room temperature and pressure. So any gas at room temperature and pressure occupies 24 decimeters cubed of volume. So this is a finding that I think was discovered by Avogadro. You might have heard his name mentioned in the Avogadro constant. Any gas, no matter what gas it is, because the particles are so far away, any gas, 1 mole of any gas will occupy 24 decimeters cubed at room temperature and pressure. So 1 mole of any gas. So that means you can use this triangle: volume of gas equals moles times 24, or the moles equals the volume divided by 24. So again, it's important to remember that the 24 is in decimeters cubed, and so is the volume. So again, often you'll be given volumes in centimeters cubed, and you'll be expected to convert that to decimeters cubed. Hopefully you'll already be familiar with that, but just in case you're not, 1 decimeter cubed equals 1000 centimeters cubed. So for example, if you had 500 centimeters cubed, then that would be 0.5 decimeters cubed, and so on. So just make sure you convert that, and that's why we've got these second two rearranged equations where we have volume equals moles divided by 24,000. If you've got centimeters cubed, that's another way to remember to make sure you convert. So in the practical we'll be looking at today, we're going to be using those 3 equations: the moles equation using mass, the moles equation using volume and concentration, and the moles equation using volume of gas. So let's have a look at the first practical. So this has been adapted from an old practical exam. So nowadays you don't have practical exams the way you used to before the specification changed. You're expected to do the practicals in class, and then you'll be examined on everything, including practicals, in your exam papers at the end of year 13. But this is an example, has been adapted from an old practical exam paper from before 2015. So this first experiment is looking at measuring volumes of gas. A student investigated the reaction between magnesium carbonate, so you've got a group 2 carbonate, and dilute sulfuric acid, H2SO4. So they've given us the formula there, and they've quite nicely given us the equation, which is a nice balanced equation for the actual reaction taking place. So it's nice that they give that to you, but you may be expected, depending on the context, to actually balance this for yourself. So the magnesium carbonate, which is a solid, was weighed out and placed in a conical flask. So that's what we've got down here. And then the student set up the apparatus shown below to measure the volume of gas produced in the reaction. The student removed the bung, added the sulfuric acid, replaced the bung, and measured the volume of gas produced. Okay, so this is the method they used. He's made a mistake in setting up the apparatus such that the volume of gas produced could not be measured. Can you identify the mistake? So I'll give you a second to just look at the apparatus and think about that. So you may remember, whether you're on GCSE or A-level, that in order to measure the volume of gas produced in a reaction using this method, this measuring cylinder must start full of water. So the mistake he made in setting up the apparatus was that he didn't fill the measuring cylinder with water. If the measuring cylinder is full of water, then as the gas is produced in the reaction, it will go along this delivery tube and enter the measuring cylinder, and it will displace, so the gas produced will displace the water in the measuring cylinder. So if the measuring cylinder contains air, then yes, the gas might displace the air, but there'll be no way for you to measure using the measuring cylinder how much gas was actually produced in that reaction. So that's the key mistake that the student made at this point. Okay, now we're going on to a few calculations relating to this. So the apparatus was corrected, and then we have 50 centimeters cubed of 1 mole per decimeter cubed H2SO4 being added to 0.843 grams of MgCO3. Okay, so I'm kind of color coding the information. I definitely recommend highlighting your exam papers, all the information that you're given, because it can be easy, especially when a long question, to sort of forget the information that you were given, especially if the question might go over multiple pages. So as we can see here, we've been given a volume and a concentration, so we can use the solution moles equation for this one, and over here we have a mass, so we'll need to use the mass moles equation for this one. Okay, carbon dioxide gas was given off and collected in the measuring cylinder. So first, calculate the amount in moles of the MgCO3. Okay, I'll just change that highlighter to keep it color coded. Right, so we need to use the moles equation that we had at the start, which is moles equals mass over mR. Okay, so we've been given the mass, 0.843. The next thing we need to know is what the mR of this substance is. So the mR of MgCO3, this, as I said, comes from the periodic table. You'll have to refer to your periodic table to get the atomic masses of each of these atoms and then add them all together to get the molecular mass, which is the MR of MgCO3. So Mg is 24.3 on the A-level periodic table. And then carbon is 12 and oxygen is 16. We have 3 of them, so we need to times that by 3. And that gives us an MR of 84.3. So now we can take our mass, 0.843, divided by 84.3, and that gives us 0.01. So that's our amount of moles in the equation. Great, so again, like I said, feel free to ask any questions as we go along if there's anything you're not sure about. I'm trying to keep an eye on the chat on both Zoom and YouTube to make sure that you guys haven't got questions I'm missing, but do let me know if you've got questions as we go along. Okay, so calculate the amount in moles of the 50 centimeters cubed of H2SO4 using the experiment. So as I said again before, we're going to use the equation that involved using volume and concentration. So moles equals volume times concentration. Remember to convert the volume to decimeters cubed. So the volume is going to be 0.05 decimeters cubed, which is 50 centimeters cubed. And then the concentration is 0.1. So that gives us 0.005, which you can also write in standard form as 5 times 10 to the minus 3. In this case, they haven't specifically asked for standard form, so 0.005 would also be fine. But as you go through A level, you may be expected more and more to use standard form, which is obviously just another way of writing these small decimal numbers that is supposed to make it a little bit easier to deal with. So we've got the amount of moles of the sulfuric acid, we've got the amount of moles of the MgCO3. So now it asks us to calculate the excess mass of MgCO3 that was placed in the conical flask. So if you're a GCSE student, you may remember learning about limiting reactants, and that's the idea that we're looking at here. So if you flick back to the equation for a sec, this shows us that we've got 1 mole of MgCO3 reacting with 1 mole of H2SO4. So based on the moles that we've calculated, we'd expect a 1-to-1 ratio to react with each other. Whichever one has more moles than the other one, it means that is going to be your extra or excess moles that won't actually react, and they'll be left at the end. So the one that has the excess is, we're going to work out in a second, they've said it's MgCO3, and that means that the H2SO4, our sulfuric acid, must be our limiting reactant. If we were to add more of that, then we would be able to produce more of our products. So we've got the moles of MgCO3 from 1, and then we've got the moles of H2SO4 from 2. So to figure out the excess mass, the excess mass, we need the excess moles first of all. So that's going to be 0.01 from question 1 minus 0.005 from question 2, and that gives us 0.005. So because of the 1-to-1 ratio, we actually have twice as much in terms of moles of the MgCO3 compared to the H2SO4, which means we're going to have this extra 0.005 moles left over. And it wants us to calculate the excess mass, so we need to convert the moles into mass. So the mass will be moles times MR. Remember, this is just one of the rearrangements of the first equation that we looked at here. So that's this one here. Great, and so moles is 0.005 times the MR, which we already calculated earlier. So that's 84.3, and that gives us an answer of 0.4215 grams. Okay, just a little side note as well, for those of you watching along or watching later after this live has gone live, I'm going to put a link in the description to these questions that I'm going through now, so that you can go through them in your own time and also have a look at how I worked out the answers as well. Okay, so the next bit then, we now know the excess mass. Now it says, show by calculation that the maximum volume of carbon dioxide produced in the experiment at room temperature and pressure is 120 centimeters cubed. Okay, so here we need to again go back to the balanced equation and realize that this is a 1-to-1 ratio for all of the reactants and products. So if we have 1 mole of the reactants, we're going to produce 1 mole of carbon dioxide, which is what we're interested in right now. And therefore, if we have 0.5 moles, we're going to produce 0.5, etc. It's a 1-to-1 ratio. So that means from the balanced equation that the amount of moles of our limiting reactant, which was our sulfuric acid, this is going to be the same, the amount of moles of CO2 gas produced. So moles of CO2 equals 0.005, or 5 times 10 to the minus 3. And then to find the volume, we use that third equation for the volume of gas. So volume equals moles times 24 dm cubed, remember? So 0.005 times by 24, and that equals 0.12 decimeters cubed, which if we times by 1,000 gives us 120 centimeters cubed. Okay, so we've proved that we expect if everything reacts the way we would expect it to. We've shown that if 0.005 moles of sulfuric acid reacts with our excess of magnesium carbonate, we're going to produce 120 centimeters cubed of our carbon dioxide. Okay, the student decided to repeat the experiment using 0.843 grams, so the same amount of mass of powdered MgCO3 this time. So it's been powdered. That's the only difference because the mass is the same. What effect would this have on the volume of gas collected? So again, I'll give you a couple of seconds to think about that for yourself. Will powdering the MgCO3 magnesium carbonate, will that have an effect on the volume of gas collected? Okay, so you may remember that powdering a solid will increase its surface area, which will increase the rate of a reaction. However, if we're using the same amount in moles or mass of that substance, then the overall amount of product produced will end up being the same. By powdering it, we're not giving the reaction more of the reactant. We're just making the reaction happen faster by increasing the surface area. So effect on the volume of gas will be none or no effect, because powdering won't affect the volume of gas, it will just affect the rate. Okay, so when the experiment in B was carried out, the volume of gas collected at room temperature and pressure was 108 centimeters cubed rather than the expected volume of 120 centimeters cubed. The volume of gas collected was measured using a 250 centimeters cube measuring cylinder, and this measurement of volume had a maximum error of plus or minus 1 centimeter cubed. Calculate the percentage error in the volume of gas measured in this experiment. So you may remember, to calculate the percentage error, we need to know the error of the equipment, and we divide it by the measurement that was taken using that equipment. So we've been told the error is 1 centimeters cubed, and the measurement was 108 centimeters cubed. So 1 divided by 108, and then times by 100 to get the percentage. So just using the calculator, 1 divided by 108 times by 100 gives 0.9259. And I would, for percentages, normally round to two decimal places. So I'll give the answer as 0.93. This didn't specify a number of significant figures or decimal places, so you could put anything up to a calculator value, anything reasonable probably from 1 decimal place up to the calculator value. But with percentages, I think it's normally standard to do 2 decimal places. So percentage error will be 0.93. So when we do these practical questions, you do need to know the kind of main core content that's in your specification, but as we've just described, we also need to know how to describe a method that you might use for carrying out this experiment. Predict what kind of issues in terms of errors there might be using that particular type of equipment, and be able to calculate percentage errors based on errors that are known to happen with the equipment that you have. So each piece of equipment has different precision, and the precision is how much error there will be for each measurement. So try to remember to learn how to calculate percentage error along with these things. Okay. I'm just having a look for any more questions before I move on. Okay, so a student made the following 2 suggestions to explain why the volume of gas collected in the measuring cylinder was less than the expected 120 centimeters cubed. I've just noticed my screen share isn't updating, so I'm just going to restart that. Hopefully. Okay, Now it's updated now. Okay, great. So a student made the following 2 suggestions to explain why the volume of gas collected in the measuring cylinder was less than the expected 120 centimeters cubed. Explain why each of these suggestions is wrong. Okay, so the student made some suggestions, but these are actually wrong. Some of the magnesium carbonate has not reacted. So think about, if not all of the magnesium carbonate had reacted, would that have an effect on the volume of gas collected? And we need to think back to our calculations over here, where we calculated that there was an excess mass of magnesium carbonate, and in fact there was twice as much magnesium carbonate as we needed. So if we didn't have all of it react, then actually it wouldn't affect the volume of gas because the magnesium carbonate was in excess. So even if it didn't all react, it shouldn't affect the volume of gas. Alternatively, we could write that the H2SO4 is the limiting reactant, and therefore the MgCO3 isn't. But I would probably prefer that first one as an explanation. Some of the carbon dioxide is still in the delivery tube. Okay, so let's have a look back at the actual diagram here. So you might think that perhaps some of the carbon dioxide would get stuck in the delivery tube, so somewhere in this section here. And while that may be true, at the end of the experiment, not all of the carbon dioxide will have been pushed out of the delivery tube. What you need to remember is that at the beginning of the reaction, there was air already in the delivery tube. So when the reaction started, the carbon dioxide that was produced would have pushed or displaced any of the air that was in the tube in the first place, and that would have been the first gas that would have collected here. So the gas in the delivery tube at the beginning was air, and it was displaced first by the carbon dioxide, and then therefore the remaining carbon dioxide at the end would have been the same amount as the amount of air that was there at the beginning. So again, this shouldn't affect the amount of carbon dioxide that was measured in the reaction. So write something like the delivery tube started with air in it, and this was displaced by the CO2. Anything that correctly explains or describes the fact that the CO2 replaced the air that was there to start with. So overall, there won't be any incorrect measurement of CO2 based on what was left in the delivery tube. Okay, a student modified the apparatus by collecting a gas in 250 centimeter cubed gas syringe rather than collecting it in over water in a measuring cylinder. So the 2 different methods was a gas syringe, which goes straight into the syringe, and the syringe moves out to fill for the gas to occupy the space, or over water using a measuring cylinder like we just did. Both the measuring cylinder and the gas syringe have the same maximum error. Explain why the volume of gas collected in the gas syringe at room temperature and pressure is nearer to the expected value than the volume of gas using the original apparatus. This one is a bit of a tough one. You need to know a little bit about the properties of carbon dioxide as a gas. And you'll know about carbonated drinks like Coke and Sprite and soda water and things like that. Carbon dioxide is a gas that can actually dissolve in water. With carbonated drinks, when you get that kind of fizz thing that happens, that's because it's been pressurized, and when we open the container, the pressure allows some of the carbon dioxide that was dissolved in the water or in the drink to be released. So carbon dioxide is a gas that can dissolve in water, and that means that if we use the collecting the gas over water in a measuring cylinder, that some of the carbon dioxide will actually dissolve in the water in the apparatus. Because it's a soluble gas. So that's why if we use the gas syringe, even though it's got the same measurement error, if all else is equal, then we may measure less carbon dioxide than expected, because some of the carbon dioxide will have actually dissolved into the water in the apparatus and therefore not reach the measuring cylinder, which is where we're trying to collect the gas. Okay. A possible reason for the lower volume of carbon dioxide was that some of the gas escaped when the sulfuric acid was added. So perhaps the bung wasn't replaced quick enough or something like that. A student suggested that this could have been avoided if the 50 centimeters cubed of sulfuric acid was added from a tap funnel as shown in the diagram. So this is our tap funnel. We open the tap and release the sulfuric acid into the conical flask, and then the gas will be produced and go up into this delivery tube and into the gas syringe as before. So sulfuric acid comes down and then the carbon dioxide gas comes out. When this experiment was carried out, the volume of gas collected in the gas syringe was now much more than 120 centimeters cubed. Can you explain why? So again, I'll give you a couple of seconds to think about this before I go through the answer. Okay, so again, these types of questions are sort of trying to test your ability to evaluate what's going on in the practical, see if you understand what's actually going on in the apparatus. So as this tap funnel and this sulfuric acid is released into the conical flask, assuming the rest is a closed system, then all of this volume of sulfuric acid, as it goes in, is going to already start displacing the air in the conical flask before any of the reaction starts or CO2 is made. And so that amount of volume that we have of this sulfuric acid, which is 50 centimeters cubed, will displace 50 centimeters cubed of air from the flask and push it into the gas syringe. So we'll have 50 centimeters cubed of air in the gas syringe due to the displacement from the sulfuric acid before the reaction even starts and we produce carbon dioxide. So the explanation, would be something like the sulfuric acid would displace the air in the flask, and we would therefore have some gas collected before the reaction starts. Sulfuric acid. Okay. And now it wants us to predict the amount of gas collected in the gas syringe. Okay, so we just have to think back to the information that we've been given earlier, where we expected 120 centimeters cubed of the carbon dioxide to be formed. That's what we've been given that information a couple of times. So we're expecting 120. And as I said, the extra gas that will be collected in the gas syringe will be 50 centimeters cubed due to that being the volume of the sulfuric acid that we have. So 120 plus 50 equals 170 centimeters cubed. Okay, so we're going to expect now to have 170 centimeters cubed collected in the gas syringe rather than 120. So in this situation, the measuring cylinder, due to the dissolving of carbon dioxide, resulted in measuring something that was too low, amount of gas that was too low. And with this apparatus, using the gas syringe and the tap funnel, it resulted in an amount of gas that was too high. So it's important to make sure that you set up your experiment in a way that's not going to produce these errors that are not going to give us accurate or valid results. In theory, the best way to do this practical would be to do it the normal way in terms of adding a bung with a delivery tube onto the conical flask without the tap funnel, and then using a gas syringe. Just making sure that you add the bung quickly enough before the reaction starts and making sure there aren't any leaks in that gas syringe apparatus. Okay, and then a final question relating to this this experiment. The experiment was repeated using the same volume and concentration of hydrochloric acid now instead of sulfuric acid. Write an equation for the reaction between magnesium carbonate and hydrochloric acid. Okay, so remember we were given the equation for the original reaction, so we can base our new equation on that, but we need to make sure that we balance it differently because sulfuric acid and hydrochloric acid will give us different balancing. So magnesium carbonate plus hydrochloric acid will go to magnesium chloride, which is MgCl2. This is one of the differences that we'll see between the original equation and this one. Remember, Cl is in group 7, so it's a 1 minus. Mg is in group 2, so it's a 2 plus, and that's why we need 2 of the chlorides in that iono compound. Plus water plus CO2. And because we have the 2 Cl's here, we need to balance that with a big 2 at the front. That means it will have now 2 H's, and that balances with the H2O's there. So that is our balance symbol equation. If you're basing it on the other equation, you might have put state symbols in, but because this question didn't ask for state symbols, you're only marked on the correct formulae and the correct balancing of this equation. Okay, what effect, if any, would using this amount of HCl instead of H2O have on the volume of gas collected? So we'll remember from earlier that the sulfuric acid was the limiting reactant. So we said that in that evaluation question. And we also looked at, when we calculated the moles, we figured out that there was fewer moles of the acid than there was of the magnesium carbonate. So that the acid was already limiting, and we have the same volume and concentration now of this new acid. And this new acid balances differently to the first acid. So the first acid, sulfuric acid, had a 1-to-1 ratio. That was H2SO4. But this one has a 1-to-2 ratio of HCl, which means we actually need twice as much HCl as magnesium carbonate to fully react with it. So if we have the same amount of HCl as H2SO4, it's still going to be limiting, but it's actually going to be producing half as much CO2 as we would expect with the H2SO4 because of this 1-to-2 ratio. So same moles of HCl as H2SO4, which you'll remember was 0.005. But now we need 2 moles of HCl for every 1 mole of MgCO3. And that means we have half as much, we effectively have half as much in order to produce the CO2. Or another way to explain it is if we look at this, the equation we've just written, we have a 1-to-2 to 1-to-1-to-1 ratio. So if we're comparing how much acid we have to CO2, again, it's 2-to-1 ratio there. So if we had 0.005 here, we'd have half as much, 0.0025 here. Whereas with the H2SO4, this would have been a 1-to-1 ratio, which would have meant we have 0.005 to 0.005. So hopefully that's another way to show, if you didn't understand the way I explained it in the first way, another way to show you that if we have this new acid HCl, we're going to only produce half as much carbon dioxide. So the same number of moles of HCl as H2SO4, but now we have a 2-to-1 ratio, so half the volume of CO2 would be produced. So if you wanted to put a value to this, that might give you extra marks. We expected 120 centimeters cubed, so now we'll expect 60 centimeters cubed. So this is quite a tough one if you're not that used to using these moles equations and manipulating them and working out moles ratios and things. But as you go through A level, this is the kind of thing you'll get more and more used to working out in terms of the amount of moles you have in the equation and how many you need to fully react. Okay, has anyone who's been watching live got any questions about any of what we've gone through so far? Just having a look and checking the chat boxes. Haven't seen any more questions since that one we had at the beginning. Okay, I was going to spend about 45 minutes to an hour online today, so I'm just going to go through the start of the next question, because it's just got some slightly different things to maybe think about. We won't manage to get all the way through it, but I think we'll make a start just to look at a slightly different way of doing the same kind of practical, again using a group 2 carbonate, but this time it's an unknown group 2 carbonate. So, a lab technician found a bottle containing lumps of white solid in the preparation room. The original label was missing, however, someone had written group 2 carbonate on the bottle. The lumps of the solid were white and pure and dry. A chemistry teacher thought she should hold a competition amongst some of her students to see who could identify the carbonate. 3 students worked in the same lab on the same afternoon and shared the same balance. So this is a statement just to try and help you to understand that we've got generally the same conditions. We're not going to have different temperatures or anything like that. We're in the same lab on the same afternoon. So what does student 1 do? Student 1 recognized that if an acid is added to a carbonate, then carbon dioxide gas was produced. She decided to measure the volume of carbon dioxide gas involved when the group 2 carbonate reacts with nitric acid. And in this reaction, we're told 1 mole of group 2 carbonate forms 1 mole of carbon dioxide. So again, we have a 1-to-1 ratio in this reaction for the carbonate to carbon dioxide. We have a similar setup of apparatus as we had before, but this time the student hasn't made the mistake that was made originally. The student has now filled up the measuring cylinder with water, which is good to see. Okay, so the student weighed out some of the group 2 carbonate and added it to a 250 centimeters cubed conical flask. Then she added 100 centimeters cubed of 0.2 mole per decimeter cubed nitric acid. So we've got a volume and concentration of nitric acid there, which means that we can later on work out the moles of nitric acid that we had. After adding the acid, she replaced the bung and delivery tube onto the conical flask and then measured the volume of gas collected in the upturned measuring cylinder at room temperature and pressure, RTP. Her results are shown in the table below. So we've got the mass of the weighing bottle and the carbonate and the mass of the empty weighing bottle, which means, as we'll see in a second in the question, if we take the difference between these two, that will give us the mass of the carbonate. Because we're taking the weighing bottle away from the two together. So that's how we're going to work out the blank box there. And then we've got a volume of acid added and we have the volume of gas collected. Okay, let's look at the questions. Complete the table to show the mass of the carbonate used. Okay, so as I said, we're going to just take the difference between that first mass and the second mass, and that gives us 0.801 grams. So 12.247 minus 11.446 gives 0.801. So that's the mass of carbonate that we used. I'll just write it here as well, in case we need it later on. Calculate the amount in moles of carbon dioxide collected in the measuring cylinder. Okay, so we were given a volume of gas, 228 centimeters cubed. So volume of CO2, 228 centimeters cubed. So using equation 3 from the start, we can work out the moles from the volume of gas. So moles equals volume divided by, and because we've been given the volume in centimeters cubed, I'm just going to write 24,000 here instead of having to do an extra conversion. So we have 228 divided by 24,000, and that gives us 9.5 times 10 to the minus 3, or if you don't like standard form yet, then it's 0.0095. Just a little side note in case you've never come across standard form before. All we're doing with standard form is basically showing where the decimal point should be. So if we have 0.0095, standard form is to write the number. So 9.5, for example, is going to be a number between 1 and 10 usually. It's usually written to 1 decimeter cube at 1 decimal place, but it could be up to 3 significant figures. And then we times it by 10 to the power of whatever we need to put the decimal place in the right position. So if we do times it by 10 to the minus 1, it will move the decimal place once, twice. We need to move the decimal place 3 times to get from 0.0095 to 9.5, which is what we wrote in standard form. So if you do 9.5 times by 10 to the minus 3, you'll get 0.095. Another way of thinking about it is 10 to the minus 3 is 0.001. So what we're really doing is we're timesing 9.5 by 0.001, and that's what gives us 0.0095. But this is the actual number that we're talking about. This is just standard form, which is a mathematical way of writing that number. That's supposed to make it a bit easier. Okay, deduce the amount in moles of the carbonate that reacted. So we were told earlier in the question that we have a 1-to-1 ratio of carbonate to carbon dioxide. So that means we'll have the same moles exactly as what we've just worked out. 9.5 times 10 to the minus 3. A little clue here is that whenever they use the word deduce, they normally do not require any calculation, or the very, very minimum, the very, very minimum amount of calculation would be required would be to times it by 2 or maybe 3, depending on the moles ratio. So deduce almost always is asking you for the same or maybe times by 2 of something you've just calculated. That's just a little clue for questions. Okay, calculate the molar mass of the carbonate to 3 significant figures. So remember, the molar mass is what is known as MR. So the MR is what we're looking for. We have the moles and we have the mass from earlier in our measurements. So the mass was what we calculated here, mass of the carbonate. So the molar mass MR will equal mass divided by moles. So this is going back to equation 1 from earlier. So we've got the equation triangle, which is moles equals mass over MR. So MR equals mass over moles. So the mass was 0.801 and the moles is 0.0095. So that gives us 84.3157, and it said to 3 significant figures, so 84.3. Things like significant figures are really important to get into the habit of getting right in the exam, because often you'll get an extra mark just for writing the correct amount of significant figures. So if the question states the number of significant figures, it's very important that you actually write that amount of significant figures. So 3 significant figures in this case is talking about either 3 significant figures before or around the decimal place. Or if we had, like, let's say 0.0095, we don't count the zeros that just come after the decimal place. We count the first significant figure would be the 9. So 0.0095 would be to 2 significant figures. So that's just the difference between significant figures and decimal places. Decimal places are strictly how many figures after the decimal place, but significant figures is from the first non-zero figure after the decimal place. Okay, so we've got the molar mass of the carbonate, and then it says hence deduce the formula of the carbonate. Right, so it was actually in the previous question, but we did in the previous question calculate a molar mass of 84.3 for magnesium carbonate. So if you remember that, then you should easily know that this is actually going to be magnesium. But the way to work it out would be to think about our metal, this group 2 metal, as maybe X or perhaps M, but I'm going to use X. So XCO3, that's going to be the formula of our carbonate. We just want to find out what X is. So we can work out, so the molar mass of this is 84.3. Molar mass of CO3 by itself, we can look at the periodic table for. So that would be 12 plus 16 times 3, which is 60. So we take the molar mass we know, 84.3, minus 60, which is the carbonate part, and that gives us what's left over, which is X, which is 24.3. And if you refer back to the periodic table, you'll find that the metal in group 2 with a molar mass of 24.3 is magnesium. So the formula will be MgCO3. If you happen to have got your calculations wrong somewhere earlier, then you would get error carried forward and you'll be given the mark for the group 2 metal or carbonate that's closest to the value you measured or calculated for your molar mass of your group 2 carbonate. Okay. We'll finish on this percentage error question. As I said, percentage error questions also come up a lot when we're looking at practicals and evaluating them. So see if you can remember the percentage error equation from earlier to work out this question. Student 1 evaluated the measurement errors in her experiment. The volume of carbon dioxide measured has a maximum error of 1 centimeter cubed. Calculate the percentage error in the volume of carbon dioxide measured in this experiment. So try and remember yourself before I write it. So we want to use the error, which in this case is 1 from the question, divided by the amount that was measured using that piece of apparatus. So we need to go back to what the volume of carbon dioxide that was measured, which is here, the volume of gas collected, 228 centimeters cubed. So 228 times by 100 to give us the percentage. So 1 divided by 228 times by 100 gives us 0.43859. And so I'm going to again do that to 2 decimal places. So 0.44 is my percentage error. So this means that we know that the base is less than 1% error in our measurement, which is pretty good. Okay, I'm just going to have a quick look at how many other questions we have and which ones we should maybe go over. Okay, we have a few minutes left before we've come to our hour, so I will just go through one more series of questions about this experiment. So just looking at how another student did try to do the same, try to identify this same carbonate. Okay, so student 2 carried out the same experiment as student 1 using the same practical method and using the same mass of group 2 carbonate. He processed his results correctly but obtained an answer for the molar mass of carbonate which was 10 grams per mole greater than what was obtained by student 1. So just one procedural error that could have resulted in obtaining this molar mass greater than that of student 1. So you need to think back to the practical and to the calculations we've done to work out how is it possible that using the same method, this student has worked out a greater molar mass than the first student. So if we think about how we calculated the molar mass, we took the mass of the carbonate that was measured in the first in the first table. So that was this mass of our carbonate here. So we took that mass of carbonate and we divided it by the moles that we worked out from the volume of CO2. Excuse me. Okay, so if this is our equation to find the molar mass, and the molar mass that he got was larger than student 1, then either we would have had to get a larger mass produced, a larger mass of carbonate used, which is probably unlikely, or in order to get a smaller moles, that would have required us to have produced a smaller amount of gas. So the only two ways in order to that he would have got a larger molar mass is either a greater mass of solid, the carbonate in the first place, or measuring a smaller volume of gas produced. And I think in terms of this practical, the fact that they set it up in the same way, I would say it's likely that it's going to be the fact that we got a smaller amount of gas due to the gas being lost somewhere along the way. So student 2 lost some gas, or some gas was lost by student 2. And this could have been, for example, by not replacing the bung quickly enough. So the bung was replaced too slowly. So this means if the bung was replaced too slowly, perhaps some of the reaction would have started and gas would have escaped before the bung was then closed to seal off the equipment and make sure the carbon dioxide went all the way through. So in order to get a greater mass, we either needed to produce, in order to produce a greater molar mass, we either had a greater mass of the solid, which is unlikely, or fewer moles of the gas based on the volume. Okay, having checked his practical book, he realized that he'd used 100 centimeters cubed of 0.2 moles per centimeter cubed of sulfuric acid instead of nitric acid. So it's the same volume of concentration as we had before, but now it's sulfuric acid instead of nitric acid. He wondered whether this was the reason for his anomalous result. So you might be, this might be something that would be important, because these have slightly different formulae, which means that sulfuric acid normally would, because it produces 2 H+ ions for every 1 molecule versus 1 over here, it may often be the case that using a different acid might have an effect. However, it says explain why the addition of sulfuric acid instead of nitric acid would not have affected his result. And this is going back to the idea of the balanced equation and which of them was in excess. So if we just flick back through the question, we need to work out from our information which acid was in, which of the things was in excess. Okay, so we know the volume and concentration of our acid. Moles equals volume times concentration. And this is actually quite easy to work out. So it's 0.1 times 0.2, which is 0.02. Okay, so if this is how much acid we have compared to how much of the carbonate we had, which is this much here, 0.0095. So this tells us that we have way more acid than we need in order to fully react with the carbonate. So this means the acid was in excess. So it actually doesn't matter whether she used nitric acid or sulfuric acid. Sulfuric acid would have the effect of providing more moles of the acid to the reaction, or in relation to how much carbonate was needed. So because the acid was in excess already from the nitric acid, then having sulfuric acid instead would not have affected the result. So acid was in excess or the carbonate is the limiting reactant. So hopefully you can start to see a kind of pattern in the types of questions that are asked about this sort of thing. You're expected to work out moles from information you're given about amounts and masses, volumes, concentrations, etc. And then evaluate things based on what errors might have occurred, what kind of errors might produce this different result or this different result, and thinking about limiting reactants and reactants in excess. The final question we'll look at is, the teacher suggested that the problem may have resulted from using the same mass of group 2 carbonate in powdered form rather than in lumps. State and explain how the use of the same mass of powdered carbonate would affect the rate of reaction and the volume of gas produced. So we talked about this again briefly in the previous set of questions. The same mass will not affect the volume of gas produced because the same amount of moles, but the powdered carbonate will increase the rate of reaction. It says to state and explain. So this is the stating, what I've just done here. The explanation for the rate of reaction is because we have the powder will increase the surface area. And therefore we have, you wouldn't be expected for 2 marks to explain it in too much detail, but the increased surface area means you have more collisions per second because you have more surfaces to react on. The volume of gas produced will not affect, the same mass will not affect the volume of gas produced because, we'll just say the volume of gas produced is not affected because we have the same mass, therefore the same moles of the carbonate. Therefore the same moles or volume of gas. Okay, great. So that's all we're going to go through today. Thank you very much for joining me. If you've joined me live, I'm going to stop my share there. And as I said, I will provide a link in the description shortly to how you can access the questions and also my annotated answers for this in case you're watching this later on or want to have a go at the questions yourself. On Sunday, Dr. Owusu will be doing the next live practical. I believe it's already scheduled on the YouTube account. I can't remember off the top of my head what that's going to be, but you can check the details on our website, boostrevision.com, or on the YouTube page, and we'll also be posting it on Instagram too. Feel free, if you weren't on this live but you're watching this later, feel free to ask us questions in the comments or connect with us on social media at Boost Revision on Instagram, Facebook or Twitter. Please visit our website to have a look at all the courses that we provide. As I said, we're going to be doing these free live streams of the practical sessions over the next month or so. But we also have AS and A2 organic chemistry courses with lots of worksheets and quizzes inside, as well as a whole series of live revision sessions that were recorded over the last 6 months that go over all of the A-level course, both AS and A2 as well. So have a look on our website to see if you want to take a look at those sessions. We also have a free course, which is an introduction to A-level chemistry, which might be suitable for those of you in year 11 who are thinking about going into AS chemistry next year, but perhaps not sure. And that free Head Start to Chemistry course will help you to bridge the gap between your year 11 GCSE studies and your A-level AS studies next year. So again, thank you very much for joining me. Please keep an eye out for our next sessions. If you haven't already, please consider subscribing to our channel so that you can get notified of the next sessions that we're going to be doing. And I hope you have a lovely rest of the week and are keeping safe and healthy at this crazy time. Okay, thanks very much again for watching and see you again soon.